In this lesson, we're going to carry on with solving rational equations. We're just going to look at a couple more techniques to help us to add to the ones we did in the last lesson, well, part 1 of this lesson, lesson 8 still. So the main thing, there's only 2 examples, and the first one, though, is what happens if we don't have a fraction equals fraction situation. Because when we did have fraction equals fraction, then we could cross multiply. But this is not a cross-multiplying situation because we got that pesky 5 stuck onto the end of the left side of the equation. So that means we can't cross-multiply. What we can do, though, is we can get a common denominator, and then we can work with that common denominator. So if we look at this equation, we already have a denominator of x plus 1, and we have x, right? These are the 2 denominators that are already here. So the way we could change this into a common denominator is we can multiply these denominators that we already have together. Now I need you to listen very carefully to what I'm about to say. When we have something like x and x plus 1, we have to take the x plus 1 as a unit. We have to take that x plus 1 as all together. So my common denominator can't be just x plus 1 because this x doesn't divide evenly into x plus 1. Those are 2 different terms, and so I have to multiply them together to get my common denominator. So every time I've got different things, just again to drive home this point, let's make another example. Say I had 1 over x plus 1 minus 1 over x plus 2 minus 1 over x plus 3 equals 1 over x. What I've got is 4 completely different denominators that don't divide into each other. In this case, the LCD would have to be x times x plus 1 times x plus 2 times x plus 3. And that's going to be really ugly, but we're not going to do that. I just wanted to use that as an example. What you need to understand is you must multiply each different denominator together and not assume things like, oh, x goes into x plus 1, because it does not. All right? So that's my word of warning. So my lowest common denominator is going to be x times x plus 1. So then I want to go by this. I think of this as having 3 terms. Term 1, or parts, with, if you want to think of it that way, 1, 2, 3. Each part has to be a fraction with this common denominator in it. So what's missing from part 1? The 2 over x plus 1. Well, the x is missing from that one, isn't it? So I need to multiply. I need to keep the part the same. I've got to keep it with the same value as x plus 1, 2 over x plus 1, but it's got to now also have an x in the denominator. Well, the only way I can keep it as a common, or the same value, is to add an x to the top as well. So if I multiply the top and the bottom by x, now I've got something equivalent to what I've labeled as part 1, but it's got the denominator of x plus 1 that I want. Let's skip over the 5 for a second. Let's just go to the 1 over x part, and I want to change that into something with the same common denominator. Well, again, if I want that common denominator, I need to have a x plus 1 on the bottom of this one as well. But I can't just add it to the bottom without adding it to the top. And so, there we go. I've added it to the top and bottom. And now I've got that common denominator for this part as well. And the highlighting, the green and the yellow, is just meant to show you, help you see where things are coming from. Let's go back to what we skipped. We had 5. That's not even a fraction. But I can think of it as a fraction. And it doesn't have any of the denominators that I want. I need to add both an x and an x plus 1 to give me the common denominator I want. So both of these have to be added to this one, which means that both of them have to also be added to the top. So that's the first thing we have to do. Now I've got them all with common denominators. I know that the factors in each denominator are not necessarily in the same order, but they're equivalent. It doesn't matter what order I multiply things in. X plus 1 times x is the same as x times x plus 1. So we have a common denominator for all of them. The beauty of doing this is that if each of these fractions have a common denominator and it's an equation, it stands to reason that the numerators can be made into their own little equation, which is true. So if 2x over x plus 1 times x plus 5x times x plus 1 over x times x plus 1 equals x plus 1 over x times x plus 1, then these numerators must have the relationship where it's equal. What I've got here is circled is true. So long and short of it is, once I've got the common denominator and see what the numerators are, I can drop the common denominators. I can just look at, I guess, think of it as just focus on the numerators. So this has to be true. 2x plus 5x times x plus 1, I just dropped the brackets around that x, equals x plus 1. I also just dropped the 1 in front of the x plus 1. This must be true. So you get the common denominator, you drop that denominator, focus on the numerators, and now we're back to just having a nice polynomial that we can solve. So expanding it out, I get 2x plus 5x squared plus 5x. I can bring the x plus 1 over to the left, changing the signs, of course. Collect my like terms. Sorry, this should have been a 5x squared here. Put things in the proper order from highest exponent to lowest. Oops, I forgot about that one. That should be a 6x. And that's all equal to 0. All right, so then we just, again, we need to solve this. So I could do trial and error, I could try decomposition, I could try whatever seems to, works best. I can't, though, when I look at this, I like trial and error. So if I was to try trial and error on this one, I set up with this little box, which you may have seen before, and I get the factors of 5x squared. Let's go with different colors. I get the factors of 5x squared here. I get the factors of 1 here. 1 times 1 gives me 1. I'm not worrying about the sign right now. And then I multiply between them. I multiply like this. This is my thinking, and I try to come up with some combination which is going to give me a positive 6x. At first, if I go like this, then 5x and 1x from those two multiplications seems promising, because I could get a positive 6x out of that, except for the hang-up that I've got this minus sign in front of the 1. So one of these 1's has to have a minus sign in front of it. So if I put a minus sign in front of this one over here on the right, then what I'd actually end up with is a minus 1x squared, which would only give me 4x. If I try the minus sign in front of the other one over here, then I'm going to end up with a minus 5x, which gives me negative 4x. So I don't have any other options as far as rearranging these goes. It turns out that no matter what I do, I can't factor this. So if I can't factor, then I can always go to my old crutch, the quadratic formula. So negative b, so negative 6 plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Negative 6 plus or minus 36 plus 20 gives me 56 under this bracket. And I get 10 on the bottom. So, square root of 56, what's that? 7.48. So I'm going to do negative 6 plus or minus 7.48 divided by 10. So if I do negative 6 plus 7.48, divide that by 10, I get about 0.15. And if I do negative 6 minus 7.48, divide that by 10, I get negative 1.35. So again, a couple things going on that aren't really related to each other. The first and most important part as far as this lesson goes is understanding what to do if you don't have a cross-multiply situation. Again, if you don't have fraction times fraction, you have to get the common denominator, drop that denominator, and carry on from there. The fact that I couldn't factor it after I simplified it was not related. It was just part of this question, but it's not always going to be a part of these type questions. And of course, I was able to use quadratic formula in this case. So that's the only example I have of one of these type 1s. So if you ever find yourself in a situation where you have to get a common denominator, you want to come back and look at this example. This one is different. I don't have to get a common denominator. Why don't I have to get a common denominator? Because we're back to fraction times fraction. I can totally cross multiply in this case. But it's just it's another one that's a bit different, so we want to take a look at this one as well. So since I can cross multiply, I totally will, because that's easiest, right? Don't have to go to all that trouble of the common denominator. When I cross multiply like this, we find this is a very interesting setup. Hopefully you recognize it as, well, look at the left side. This is a difference of squares. We got a perfect square. We're multiplying two binomials together that are exactly the same, except one's positive and one's negative. That is the factored form of a difference of squares. If I multiply this out, what I get is x4, or x to the 4, plus x squared minus x squared minus 1. And I'll do the right side in a minute. Simplifying that, these two middle terms cancel out like they always do in difference of squares. I have x to the 4 minus 1. Okay, on the right-hand side, we got the exact same thing going on. We got two binomials that are exactly the same, except with different signs. So we're going to get 4x to the 4 minus 6x squared plus 6x squared minus 9. Two middle terms are going to cancel out again. And I got 4x to the 4 minus 9. This one seems to be simplifying down rather nicely. If I bring everything to the right side, then I end up with 3x to the 4, my bad. 3x to the 4, sorry, lost my train of thought, plus 8. Plus 8, sorry, minus 8. Totally lost my train of thought. Minus 8. Okay, there we go. I'm feeling good about that. What's beautiful about this one is that the value x only shows up once. When you see something simplified down to an equation where the variable only shows up once, it doesn't matter that it's got the exponent 4 on it. It's that we only see the x once, as opposed to, say, something like this. Say I had 3x to the 4 minus x minus 8, or something like that. As soon as I have a second x there, that messes things up for me. But I don't have anything like that. I've got a nice simple one with just a single occurrence of the x. And why this is so nice is because I can isolate this x. Remember back in grade 9 when we were able to just isolate a variable just move everything to the other side and get that variable by itself, but then things started getting tougher in grade 10 because of quadratics. That's when we started factoring things. Grade 11, it was worse. Grade 12, we got even more going on. In a sense, we're back in grade 9. We've got just one occurrence of the variable. Let's isolate it. So let's bring that 8 back over to the other side. Let's divide both sides by 3 to get rid of the 3. And then what we can do, we've got x to the 4, we can take the 4th root of each side, because the opposite of raising something to the exponent 4 is to take the 4th root. And we've got x by itself on the right, which is very exciting because it really wasn't much work to do that. And in our calculators, we can do 8 divided by 3, and then we can take the 4th root of it, and we get 1.28. Let's round it to. So our answer is 1.28. Oh, but wait. There's one other thing we have to consider. Remember how, just as an aside again, let's go to something easy. Say we had x squared equals 4. If I wanted to find out what x is, I could take the square root of each side, but I had to put a plus or minus in front of that square root. So my answer for x squared was actually plus or minus 2 in this simple example. Because if we check it, 2 squared equals 4, but negative 2 squared also equals 4. That's a feature of any even exponent, or when I'm solving for anything to an even exponent. So 2 is obviously an even exponent, but 4 is also an even exponent. So because of that fact, the fact that I'm taking a 4th root, I need to put a plus or minus in front of that, and there's actually 2 solutions. Plus or minus just means I've got 2 solutions there. I've got positive 1.28 and I've got negative 1.28. If I were to take positive or negative 1.28 and put it back into this original equation, both of them would satisfy it. So we have to consider that as well. So just another things to look out for when we're solving rational functions.